So we are starting chapter 10. So if you remember, we did the first half of chapter 10 before, went a break, and that was over conic section. So this is going to be the second half of chapter 10, which is going to be over parametric and polar equations. Today we're starting in 10.6, and this is parametric equations. So, most of us probably have not heard of the word parametric equation, but have we heard of the word parameter?
Yeah.
Hopefully. What does a parameter mean?
The house.
Perimeter. That's perimeter. Not quite. What is a parameter? Like a condition, right? Or like a guideline or a restriction. Agreed? So we can kind of think about it like that. A parametric equation is going to be an x and y equation.
I thought parametrics were the guys in the ambulances.
Those are paramedics. And they're both going to be in terms of a parameter, or basically a restriction or a guideline, and that parameter is going to be the third variable. And our plane curve is going to be the graph. Of a parametric equation. And contains orientation, or contains yellow? How did I put on the other one? The orientation or direction represented using arrows. So your parametric equations, graphs are going to look really similar to just your normal graphs, but they're going to have little arrows on them. So the reason that we use these are basically when we need to describe two things in terms of something else. So a lot of times in all of the problems that we work, we've described like horizontal and vertical motion, right? But sometimes we might need to know what the horizontal motion was after a specific time, or what the vertical motion was after a specific time. So that's why a lot of times our parameter is going to be the variable t, because most of the time we're looking at that third variable being with respect to time. Question? Let's look at an example. Alright, so it says sketch the curve by the given parametric equations. So we have x equals t squared minus 4, and y equals t divided by 2. And they tell us that t is in between -2 and 3. So we have two equations. One's an x equation, one's a y equation, and they're both in terms of t. So if we're just starting by graphing something, and we don't know how to graph it, what do we usually start with?
Like input, output.
So a table, right, or chart. Yes, agreed. Except this time, what's our input need to be? Well, what's our variable for our input? T, right? And then what's our outputs? X and Y. So instead of a T chart, we're going to have an H chart. Because we have 3 variables. We have t's, we have x's, and we have y's. Y'all with me? But yes, bless you, our inputs need to be between -2 and 3. So we're going to plug all of those in, but we have to plug them in separately for x and y. So if I plug in -2 in for x, what do I get? So if I plug it into the t for my x equation, not into the x.
0.
We get 0. Are we all okay with that? If I plug it into my y equation, what do we get?
-1.
-1. If I plug in -1 into my x equation, what do we get?
-3.
And into our y?
-1.
Okay. If we plug in 0,
-4.
and?
0.
If I plug in 1,
-3.
and?
1/2.
Okay. We plug in 2,
0.
and?
1.
And then we plug in 3,
5.
and?
1/2.
3 halves. Yep. Alright. So what's our first point? Just looking at the XY stuff.
0, -1.
Alright, so I'm going to graph that just like I normally would for a normal point. I'm graphing it at 0, -1. Are we all okay with that? Then what's my next point? Okay. And then?
-4, 0.
Okay. And then? Okay. Then 0, 1. And 5, 1.5. So what do we get?
Oblique parabola.
It's like a sideways parabola. But now, what did we say that our parametric equation has to have?
Like arrows with orientation.
Correct. And that's where our t's come into place, is that we're looking at things basically with respect to time. So my starting point was 0, -1. And then we went to my next point, which was -3, 1/2. And then we continued. So we draw our arrows in the direction that our t is moving from smallest to largest. Like a fish? Ah. Questions on that? Yes. No. Maybe? So far, so good? Alright, so sometimes we want to eliminate the parameter. Okay? So eliminating the parameter is finding the x, y, or rectangular equation with the same graph. Why is it called a rectangular equation? What looks like a rectangle? The graph doesn't necessarily look like a rectangle. However, I'm dealing with 2 variables, right? so like a length and a width, so it would make a rectangle, right? When you have 2 dimensions. So that's why they call it your rectangular equation, which it just means like your normal y equals stuff with x's. That's all it means there. Okay? Now, we do have to do some steps most of the time when we want to eliminate. Okay? So if we want to eliminate, our first step is going to be to solve for the parameter in one equation. Then you're going to plug the results
So it's like substitution.
into the other equation. And then lastly, we simplify. Alright, we're gonna look at an example. So this says sketch the curve represented by the equations. It gives us an x and a y in terms of t by eliminating the parameter and adjusting the domain. So what do we need to do first?
Solve for one
Yeah, so overall, what is our goal?
to get it where we need to.
So to eliminate the parameter, right? And then we're going to graph it, yes? So, we do need a step 1, we need to solve one of those for t. Which one? It might be easier to solve for t. Sure, we can go with that one. So what would I do if I wanted to solve that for t?
Multiply t plus 1 on the other side.
Okay. And then,
Bring t, no. Maybe. Can we bring y over to the right?
you could divide it.
Yeah, that's what I meant, probably. No, this isn't fun anymore. Can you bring t to the right now? Yeah, bring y back. I'm like, wait a minute.
So what's the problem? We have how many t's in that one?
2.
2. So it's not very much fun to solve for, right? Because if one of them was squared, then you would have a quadratic, so we could do it that way, but this time we don't. So what one might we start with instead?
X.
Let's go with that one. So this time, what would we do?
We multiply both sides by square root of t.
So I am going to want to square it eventually, but the square root has to be completely by itself before we can do that.
Multiply x.
So then we need to divide by x. And now we can square it. So what do we get?
T plus 1 equals 1 over x squared.
Okay, so then what does t equal?
T equals 1 over x squared minus 1.
Okay. Did we solve for t?
Always.
Yeah. Then what do we want to do with that?
Plug it into y.
We want to plug it into y? Or
Plug it
plug it
for
into
t.
the y
Into the t on the
equation?
y.
Okay. Agreed. So I would have, excuse me, 1 divided by x squared minus 1 divided by 1 divided by x squared minus 1 plus 1. So what happens on bottom?
It stays, no, it
Reduces. So that we just have 1 divided by x squared.
Yeah.
Okay. So then what do we want to do?
I'm the top and the bottom line.
We cannot because I have subtraction in the top.
Oh.
But what we could do is that this is dividing by a fraction, right? So we could also multiply by the reciprocal, which would just be x squared. So then we get 1 minus x squared. Because when I distribute it to my first one, my x squared is reduced, and then negative 1 times x squared is negative x squared.
Wait, can you put in y and it's supposed to be?
We can't do mx plus b because it's not a line. It's going to be a quadratic.
We don't need to put it in that form.
Now if it's not a line, I can't.
Can I put it in that order almost?
I mean, if you wanted to do negative x squared plus 1, you could.
Okay.
If it makes you happy.
Yeah.
Okay, then go for it. Alright, so then I eliminated the parameter. What's my next step?
Simplify.
Well, I did that. I eliminated the parameters. Look, I did all the steps in eliminating the parameter. But what's the next part of my question says is to graph it. Okay? Not yet, because I know how to graph that. That was the whole reason of eliminating the parameter is that we can just graph this as it is because I should know what 1 minus x squared graph looks like. What does it look like?
Okay.
Not to the left.
Right, because I forgot to. It's down. There's.
Nope. It's been moved
I
up
moved up because it's.
1,
That's why I put it in y equals mx.
but it's facing down because it's negative. You agree?
Yeah.
Because it would be like negative x squared plus 1. So my k value is 1, but my a value is negative. So I've moved my vertex up 1, but then it's facing down.
I wasn't there. I felt rushed.
Okay. Yes, we're on the timetable. Alright, so that's the second part, but what's the third part say? Adjust the domain. Okay, so remember that we started with a parametric equation and we eliminated our parameter. But that means that what we're saying is that this graph, right, so that's what we said, is when we eliminate it, we're finding the equation with the same graph. Agreed? So my graph of this equation has to match what the graph of my parametric equation would have been as well. Does that make sense? The problem with that is notice where my t's are. I have a t inside of a radical, and I have a t inside of a fraction. Are there going to be restrictions on t? Do radicals and fractions make restrictions? Yes. So we have to look at how that would affect the graph because I have to make sure that those two graphs would still look the same. Does that make sense? Okay. So what restrictions do we get from our x?
There's a square root.
There's a square root. What happens with square roots?
It can be negative. No.
Mm-hmm.
Yeah, it can be negative.
So how do I write that?
Plus or minus.
No.
Uh,
How do I ensure, like how do I write algebraically?
a line x, another line, x and equal. Oh no.
Not quite.
X is greater than 0. Right.
Correct, except not just x. What has to be greater than 0 this time?
T.
Not just t.
X and T.
Nope.
Every.
The line.
So what causes issues when I have a square root? What's not allowed to be negative?
The thing inside.
The thing inside, right? So what's
Oh, yeah.
inside the radical for x?
T plus 1.
So t plus 1 has to be greater than 0. Now-
Say T has to be greater than negative 1.
We're gonna solve for it in a second. So normally it would be t have to be greater than or equal to 0. Okay, except where is that radical located? The denominator. So in this case, it can't equal 0 because it's in the denominator. But if it was just the square root of t plus 1, then you would put an equal to bar. Does that make sense? So then yes, now we're just going to solve our inequality. So we get that t has to be greater than negative 1. Okay with that? So for my y equation, what restriction do we have from that?
It can't equal 0.
Not what can't equal
T
0?
plus 1 can equal 0.
T plus 1 can't be 0, which means that t can't be what? Negative 1. Did we already take care of that from my first one?
Yes.
Yes. So t has to be greater than -1 would be my restriction. Are we okay with that? What?
It's covered by the top of the stuff listed.
No. You would if for some reason it was like a separate, so like say t couldn't equal 2, right? We would have to go from -1 to 2, leave out 2, and then go from 2 to infinity. Like you have to include both of them, but because our first one already takes care of the second one, we don't have to add it in. Does that make sense? Okay. So now we have to figure out how does that restriction, so we said that this is going to be our restriction, how does that affect my graph?
The left side.
So most of the time we're going to come back to looking at the like little chart that we looked at before. So we have t, x, and y. Now, we're not graphing the whole thing, so we don't need to plug in like a ton of numbers, but we do need to plug in enough that we know how that restriction is going to affect it. Does that make sense? Okay. So if I went ahead and tried to plug in -1, what would I get for both of those? They would both be undefined, which is why they were a restriction, right? But then going up, if I plugged in, say, 0 next, what would we get? X equals what? And y equals 0. Okay? Now, if I plug in 1 next, I'm going to get a what on the bottom? A square root of 2, right? And that's going to be a really weird decimal, so probably don't want to plug in that. What's the next number that might be a little bit easier to plug in?
3.
3, okay. What would I get if I plug in 3?
3/4.
So 1/2 for x and 3/4 for 3/4. Yes? Okay. So now we need to think about like how that pattern would continue. Okay? So as my t values get bigger and bigger and bigger and bigger, what's going to happen to our x and y values? They're going to shrink. Specifically, what are they going to shrink towards?
A very small number of 0.
Yeah, well, what is x getting closer and closer to? 0, right? So notice that what's happening is, so this is at 1, 0, right? But if I plugged in smaller negative fractions, right, we would get bigger and bigger x values, right? So I would get stuff that's going this way, agreed? And we said that it's getting closer and closer to x equaling 0, but it's never going to quite reach it. So my graph is just going to be the right side of that. Does that make sense? Yes? Do we see that as my t values get bigger, my overall x value gets smaller, and it specifically gets smaller closer and closer to 0. And remember that our direction goes from smallest to biggest. So if my bigger t values are putting me closer to x equals 0, I know that I'm going to the left.
Okay.
Does that make sense? But notice that there's never going to be a way for me to get a negative x value because of my radical, which is why we know we can't go past that 0.
Okay. So the adjusted domain version would just be like that.
The red part, yes. So here, let me see if I can. Does that help? That would be my graph. Somebody said question.
Why do you know what direction it's going again?
So, remember we said that my t values are what give us direction. We have to go from smallest to largest. Yes? So, notice that if I plug in 0 for t, I would be at 1, 0, right? But if I plugged in things that were between that, so we're talking really small negative numbers, yes,
Yeah.
that would make my denominator a really small fraction, right? Which means that the overall number would be a bigger and bigger and bigger number, yes?
Yeah.
Okay, so that means that here I'm looking between -1 and 0, I'm getting really big x values. So that means that I'm starting at really big x values. As my t values get bigger, my x values are going to get smaller. So that means that I know that I'm going from big x values to small x values, because I have to go from smallest to biggest for my t values.
Okay.
Does that make sense? So it doesn't change what the graph looks like, it just gives you the direction basically that your path is following.
Okay.
You with me?
Yeah. Okay.
Other questions? Yes. No? Okay. Want to look at another one? Alright. What's different about this one?
Cosine.
Trig function.
We have trig functions, which we know all about those, right?
Angle curve.
Yes, it is an angle parameter. So theta is our parameter this time instead of t. So what's our first step to eliminate the parameter?
Isolate theta.
Isolate theta this time. How are we going to isolate theta?
Inverse trig function.
Do we want to do an inverse trig function?
Probably
Oh,
not.
Is it going to be very pretty to do an inverse trig function?
No.
No. So let's see how far we can get without doing an inverse trig function. So if I have x equals 3 cosine of theta, what would I do to solve?
Divided by 3.
Okay. And then what would we do after that?
Leave it.
Leave it. Okay, because we would take our cosine numbers at that point, so we're going to leave it as it is. Now, what about our other one for y?
Same way to be able to 4.
Okay, so I would have y divided by 4 equals sine of theta, yes? Now, notice that we have two things. One equals cosine, one equals sine. Agreed? So wouldn't it be nice if we knew of an equation that related sines and cosines together? So we don't want to use that one because that throws in a trig function that we don't know anything about. Is there another equation that only has sines and cosines in it? Sine squared plus cosine squared equals 1. Yeah, our trig identity. Woo.
I hate trigger identities. Why can't the things just be the things they are?
So, do we know what sine is?
Yes.
Yeah, it's y divided by 4, yes? So we can plug that in now and then just square it. Do we know what cosine is?
Yeah.
So we can plug in x divided by 3 and then just square it. So now we basically solved for 1 and plugged them in. So now what do we need to do? Simplify. So we get y squared divided by 16 plus
X squared divided by 9.
what type of equation is that?
Fractions.
Yeah, specifically what type of graph is that?
Circle.
Not a circle.
Ellipse.
It's an ellipse. Not an eclipse.
It's a triangle.
So remember, it is going to be a conic section. So remember, like our little flow chart was, are both of my variables squared? Yes. So it can't be a parabola. Okay. Am I subtracting? No. So it can't be a hyperbola. Are my numbers the same? No. So it can't be a circle. So my last and only left option is then for it to be an ellipse.
Yeah, I read, I see that somewhere.
Okay, so where is our center center before that ellipse?
4,
3, 4.
3.
Not our center. Remember, your center was your H's and your K's. That was if we were subtracting
Origin.
stuff. So this time it's at the origin. Because I don't have subtraction on the inside of my square. So it's just at 0, 0. So then,
No, that's
how far left and right are we going to go?
4 and 3.
How far left and right? Just left and right. 3. 3 each side. Because that's what's underneath my X. How far up and down are we going to go? 4. Taking the square root of our denominator.
Somebody go train.
Okay, and then I'm going to make an ellipse. My units are slightly off, so it's going to be a little funky looking. That's
It looked like
okay.
a face.
Kind of. So that would be our ellipse. So that's our graph. However, what are we forgetting if this is a parametric equation? Our arrows. So remember, that's the
Oh, yeah.
difference between just a normal equation and our parametric equations. We have to have arrows. Okay? So again, we're just going to do a couple of test points just to kind of give us the direction. However, we can use any numbers we want that are within our restriction. So what do we want to start with?
2 words.
Pi.
Oh. It might help to start with the first number.
0.
So 0. What do we get if we plug in 0 to cosine? 1.
Oh, oops.
Unit circle.
Yeah.
Cosine of 0 is 1, and then I would do 1 times 3 is going to be 3.
Huh?
And then y is 0.
So if cosine,
that.
I'm plugging in x equals 3 cosine of theta. I'm plugging in, sorry, this should be a theta, not a t. But I'm plugging in 0 for theta.
Oops.
So then, if I plug in 0 for my theta on my sine equation, what do we get?
0.
That one we do get 0. Now, what type of numbers are our theta restrictions? Oh, they are not integers. They are radians this time because we're plugging into sines and cosines. So what might my next number be? Before pi.
Pi over 2.
Pi over 2. Now, when I plug in pi over 2 to cosine, what do I get? 0. And when I plug in pi over 2 to sine, 1. 1 times 4 gives us 4. And then if we did pi next, it would be negative 3 and 0. And we should get the idea after that. So notice that I'm starting at this point, right? 3, 0. And then we're going up to 0, 4. And then we're continuing on. So what direction are we moving?
Counterclockwise.
Counterclockwise.
The positive direction.
It's the whole thing.
Yeah, I just stopped at pi because from there it's going to continue going. It's not like it's going to turn around or anything like that. That's only if you had restrictions that like cause you to not be able to do things. We don't have any fractions or radicals this time. We just have trig functions. So there's not anything that would make us like have to get rid of parts of it.
Are we going to try
We have one last example. Yep. So on this one, basically we're working our way backwards now. We're starting with a rectangular equation, so y equals 1 minus x squared. And we're going to find a parametric equation, but they give us the parameters that they want us to use. Yes?
Yeah.
No? Maybe. Okay, so on part A, they tell us that they want t to equal x, right?
Yes.
So if x equals t, yes?
Yeah.
Is that an equation of x in terms of t?
Yes.
Yes, so that's my first equation, or my parametric equation. Yes.
Yeah.
So then what else do we need in order to have a full parametric equation?
The y part.
The y part, and the y needs to be in terms of t. So basically we're going to work our way backwards. So like last time when we were trying to eliminate the parameter, we got rid of the t by substituting in for our x, yeah? This time we're going to substitute in a t for our x. So what do we get?
Y equals 1 minus t squared.
Agreed.
Oh, are those like two separate questions?
Yes, so this is part A. So if I use t equals x, those are the equations that I would get.
Oh, okay.
And then for part B, if I instead use t equals 1 minus x,
Oh, that's it.
yeah, that's my
I
answer.
like set them equal to each other.
No, no.
It's like x equals 1
So technically, you can use any parameter equation that you want for t, if it doesn't give you a specific relationship. Does that make sense? Like sometimes you'll have a specific relationship between like time and your x and your y, but if you don't, you can create an infinite number of parametric equations based on t values. So how would I get my x equation here on my second one? I should use solve for x. So add x, subtract t. Okay, so that would be my first equation. And then what do we need to find? Plug it in for y. This time we are going to have to do a little bit of simplifying. You do have to FOIL. So we get 1 minus 2t plus t squared. So what does y equal?
A scaling number.
No,
Negative 2t plus 2 squared.
not quite.
Lines and numbers.
Positive 2t minus
Oh.
t squared,
Yes.
because we're subtracting all of that.
Yeah.
So you have to FOIL and then distribute your negative.
What did you just like? Difference of cubes.
It's not a difference of cube.
Where's the cube?
There's no cube.
There's no cube.
Where's the square?
It's squared, not.
Wait, so it's equal. Okay.
I just squared it and
Oh.
then simplified.
Okay. Oh.
Other questions?
Oh, that's how we got here.